Have you ever submitted an answer to a question that you thought was correct and had your teacher or supervisor immediately say something like, "Wow, that's way too high"? As you spend more and more time solving engineering problems in a certain field, you'll gain an intuition of what answers seem reasonable. Before that happens, there are a few things you can do to make sure that the answers you give for certain problems are within a reasonable range. This will help both decrease the number of obviously wrong answers that you give and speed up the time it takes for you to build your engineer's intuition. Today I want to talk about estimation, dimensional analysis, and scale. You've probably seen these topics in other classes, but I want to talk to you specifically about how to use them as engineers to double check your work and make sure your answers are reasonable. This is very important because I've found that many times students can be off in their answers by several orders of magnitude. These mistakes often happen during unit conversions. If you have a general idea about what the answer may be, even within a couple orders of magnitude, you'll be better equipped to avoid very common mistakes I see in classes. First, I want you to watch the video Fermi estimation posted on the course webpage. As you're watching, write down the answers to the following questions. First, what is Fermi estimation? And two, how can you use it in engineering classes? Go watch that video and then return to this one. I hope that you have realized that you can use relatively simple, quick estimations to make a first approximation of what your answer should be. This can be very powerful if you want to do very rough, quick calculations to see if an idea you have is reasonable before spending time researching specific values and coming up with complicated models. You may also use estimation after you finish a problem to check your answer. So at the end of this lesson, you should be able to do the following. First, make rough order of magnitude estimations for seemingly complex problems. Two, define units and dimensions and relate those to engineering problems. Three, have a rough idea of relevant scales of things, including volumes, flow rates, and power. And four, I'm going to show you 4 techniques to check your work. The Fermi estimation video gave you a good introduction to estimations. I know you've done these before in math classes, and I hope you practice these and work them into your problem-solving strategies. Next, I want to discuss dimensions and units. As you know, measured quantities have both a value and a unit. For these numbers, you should always report both the value and a unit. For example, 1 minute, 97 milligrams per liter, 70 kilograms. Each of these values is basically meaningless without the unit, so don't forget your units. You need to put units both in your answer, but you should also be keeping track of your units as you're working problems. This is going to save you from so many mistakes. A dimension is a property that can be measured or calculated by multiplying or dividing different dimensions. Units are denominations of dimensions. For example, a minute is a unit of the dimension time. Milligrams per liter is a unit of the dimension concentration, and kilogram is a unit of mass. As you've learned in other classes, values can only be added or subtracted if the units are identical. This is related to the concept of dimensional homogeneity. That is that all terms on each side of the equation must have the same dimension. If you want to add 2 numbers with different units, you can, if they have the same dimension. However, you would need to use a conversion factor to convert the numbers to the same units. For example, we may want to add 7 meters and 10 centimeters. We can do this because both numbers have a dimension of length. However, we need to convert our 10 centimeters to 0.1 meter, and then we can arrive at our answer of 7.1 meters. So while this seems very simple and straightforward for numbers, and you've probably done this in other classes, it also applies to equations containing variables. In some instances in this class, you'll be asked to configure your own equations. Whenever you do this, make sure that they are dimensionally homogeneous. That is, every term in the equation should have the same units. It's an excellent way to check your work. Also, as you're solving an equation and plugging numbers into it, also use the units. Use dimensional analysis as an additional check on your work. Just to demonstrate this topic, let's take an equation for population growth. So this is going to be a relatively simple equation for population growth. Basically, here we have PT, which is the population at some time t, and that's going to be in units of number of people. P naught is the population at time 0, which will also be in units of number of people. And then we have a growth term where K is a growth rate and T is going to be the difference in time between time 0 and time T. And I think I should mention that this is just one of several types of equations for population growth. So our growth rate is going to be in units of people per month, and then we have our time. So in this example, we'll just choose P naught, the starting population, as 1 million people, and we will choose a growth rate of 500 people per month. So 500 people move to our city every month. And we're interested in a period of 20 years. So all we have to do is just, plug everything into this equation. I'm sure you're very comfortable doing it this way, but what I want you to take note of is how I incorporate units into every part of the equation. So I have 1 million people. I have, and then I will add that to 500 people per month. And then I need to multiply that by 20 years. And because I'm keeping really nice track of my units, I'll notice that I need to rectify the difference between years and months. So I'm going to multiply that by a conversion factor, and in each year we have 12 months. And so I'll go back. Now that I've plugged everything into my equation, I need to make sure everything cancels, and I have people in each term. So P20 will be number of people, 10 to the 6th people, and then my last term that incorporates the growth rate and time is also going to be in units of people because the months and the years cancel out. And in the end, what I get is that over these 20 years, I have had 120,000 people added to my city, I guess for moving there or through being born there. And so then my new population 20 years down the road is going to be 1.12 million people. Here are a few examples of some different units. The numbers are approximate, and some of these have quite a wide range of values, but I want to give you an idea of some orders of magnitude. So, for example, volume is going to be cubed length, or the dimension of cubed length. A water bottle, relatively large water bottle, is going to be 1 liter. The Nalgene's that are very popular are 1 liter. This is 1,000 milliliters or 1,000 centimeters, or 30 fluid ounces. For some reason, I see a mistake that a lot of people seem to make is that 1 liter equals 1 meter cubed, which is definitely not the case. You can imagine like 1 meter cubed, you know, a meter is like, it's like this. I have to stretch. A meter is like this, right? And so if you cube that, it's going to be 1,000 liters, not 1 meter, or not 1 liter. Next we have a pond. So a pond might be about 100 cubic meters or 100,000 liters or 25,000 gallons. A lake is much bigger. Let's take like maybe a medium-sized lake and call it 1 mile cubed, which would be 3 kilometers cubed, or 10 to the 11 gallons, or 10 to the 12 liters, or 10 to the 9th meters cubed. And then you have something as large as an ocean. So that's going to be like 10 to the 9th kilometers cubed for the Pacific Ocean, or 10 to the 18th meters cubed, or 10 to the 20th gallons. So let's say you're designing a reactor and you calculated a reactor volume of 250,000 liters. Is that reasonable? Think about that size compared to a water bottle, pond, lake, or the ocean. So here's some examples of flow rates. So we've got a stream, fairly small, 10 cubic feet per second, or 10,000 liters per minute. A larger river might be 10 to the 6th cubic feet per second, or 10 to the 5th meters cubed per second, or 10 to the 9th liters per minute. If we talk about energy, we're looking at like a candle or like an incandescent bulb. You know, there's quite a range for some of these, but something like 100 watts, or 300 BTUs per hour. And then a power plant might be like 1,000 megawatts, or 10 to the 9th BTUs per hour. A single wind turbine might be like 100 kilowatts, or 10 to the 5th BTUs per hour. So there are some examples of volumes, flow rate, and energy. I recommend that you, whenever you encounter a unit that you're unfamiliar with, perform this exercise. Look up some examples of systems exhibiting that variable and note the order of magnitudes of the value. This will help you familiarize yourself with appropriate values, and it will help you determine whether or not the answers that you get when you're making calculations are reasonable. Finally, I want to go over 4 techniques you can use once you complete a problem to make sure it's correct. Although these techniques take a little extra time, using them will help you eliminate unnecessary mistakes. So first, double check units and conversions. You can do this while you work by keeping track of units in your dimensional analysis. Be sure to write your units down and make sure they cancel when they should. You can also back substitute. This is a way where this is when you plug your number back into the equation, and it's a good way to check to make sure you didn't make any algebraic or calculator errors. You can also do an order of magnitude estimation. Quickly go through your work and make sure the answer is about the right order of magnitude. And then finally, you can ask the question, is this reasonable? So compare your answers to values you know are like in about the same range. Are you within a reasonable range? So this concludes this video. Now you should be able to make rough order of magnitudes estimation for seemingly complex problems. Build your confidence trying this out. So you can make estimations for different things and then look up the correct number. See if you're close. You should also be able to define units and dimensions and relate those to engineering problems. starting today, if you're not already. Write your units down every time you do an engineering problem. Number 3, you should have a rough idea of the relevant scales of things, including volumes, flow rates, temperatures, pressures, lengths. I only gave a few examples. You should look up others whenever you encounter an unfamiliar unit. And finally, use these techniques for checking your work. It's going to make your life so much better, and it's going to improve your grades. A win-win. So check your work. Thank you.